All right, I think, Rachel, you want us just to continue, yes? Okay. Wonderful. My name is Becky Peterson. I'm an assistant professor in electrical and computer engineering, and it's my honor to introduce our next speaker, Professor Roy Clarke. Professor Clarke is the Marcellus L. Wiedenbeck Collegiate Professor of Physics and Applied Physics here at University of Michigan. He received his bachelor's and his PhD degrees from Queen Mary College at the University of London in the UK. And before joining the faculty here, he worked at the University of Cambridge at the Cavendish Laboratory and accepted a fellowship at the University of Chicago. Here at Michigan, he was the founding director of the Applied Physics program, which is now celebrating its 30th anniversary this year in 2017. And as I think many of you know, the Applied Physics program, through its interdisciplinary environment and its commitment to recruiting excellent and diverse students, has had a transformative impact on materials and physics research here at the University of Michigan and far beyond. For his work in STEM mentoring, he's been awarded several different mentoring awards, the Emmis and Moore Faculty Award in 2006, the Sloan Foundation Mentor Award in 2008, and a Presidential Award for Excellence in STEM Mentoring in 2011. In terms of research, he's a condensed matter experimental physicist, and he works on innovative deposition and in situ characterization of nanostructures and superlattices, which has opened up lots of new avenues for scientific exploration in the kinetics of epitaxial interfaces and their applications in electronic, optical, magnetic, and ferroelectric devices. In addition, he's been active in several startup companies, including K-Space Associates, located here in Dexter, which started as a research spinoff in 1992 and is now a leading supplier in semiconductor metrology tools. His research accomplishments have been recognized by his election to a Fellow of the American Physical Society. So today he'll be talking to us about ultra-fast, ultra-small nanomaterials for femtosecond lasers. And please join me in welcoming Professor Clarke.
Thank you, Becky, for that very nice introduction. And thank you to Rachel for organizing this event and for many wonderful years of collaboration while we're at it. A lot of people previous speakers have alluded to an important thing about Michigan. It struck me that a lot of people have asked the question, why is it so great to work at the University of Michigan doing this kind of science in materials research? My take on this is that Michigan, it really values interdisciplinary collaboration. And over the years I've been at Michigan, this has grown and grown. And there are programs that encourage this kind of collaboration, like the macro program, like the applied physics program that I'm associated with. And it's this kind of recognition that science is highly interdisciplinary, especially materials research, that really makes Michigan a great place to work. And I can think of no real better example than how these two fields of materials research and ultra-fast laser development, which, by the way, Michigan has a wonderful history, most of you know this, in the development of high-field science, and in particular in laser development. The lasers that Palab just described are one aspect of that. Michigan's had a long and distinguished history in that area. And I'm going to tell the story a little bit in the time I have, how these two fields of laser development, especially at the high field end of the business, and materials research came together to basically produce a new field of inquiry into how nanostructures can be made using lasers, and what kind of physics goes on there, what kind of opportunities exist for the future. I included this picture here because I want to say how great this was, that this just happened this last week in Australia. Michigan got to the number 2 for the first time in 27 years in the international solar car race, and there's a picture of their car, and that's there to remind us that sometimes smaller can be better and faster than bigger. So that's the new design, and we're hoping next year our students will get to number 1 and get the gold. I think they will. Now, many of you know Sherrod Moreau, who came to the University of Michigan from Rochester with a group of laser development scientists, including Ted Norris and others. And basically, why did Sherrod come to Michigan? My answer is, well, he probably has his own, I'm sure he does, but why did he come to Michigan to essentially implant on the campus of the University of Michigan this effort, which was to last for 20 years or more? Because he saw a lot of opportunities for application of these lasers, not only in engineering, where his home department is electrical engineering, but also in physics, in chemistry, in the medical field, ophthalmology, and a whole host of other fields, nuclear engineering, where Michigan could play a role and develop some of these exciting applications. And I want to say that the area that I'm going to talk about today, which is applications in the field of nanomaterials research, has been one of the areas that I've been involved with on and off for at least 20 years. And all of this development in nanomaterials made possible by a development that Sherrod Moreau was responsible for. And some of us call this Moreau's law, kind of mimicking Moore's law as a logarithmic development of a field over many years. And the big development in this field that Sherrod was responsible for is the development of chirp pulse amplification. Very simply, this is basically take a laser pulse, stretch it out through some dispersive device like a diffraction grating, stretch it out, amplify it, make it much taller, and then shrink that back down again with a reverse process of dispersion. And you end up with an enormously enhanced energy density in terms of watts per centimeter squared with this kind of process of amplification, stretching, amplifying, and then compressing the pulse. And it's this ground shift in the science here, in the technology, that CPA led to. And that occurred around about 1990, which was the time that Sherrod came to the University of Michigan campus with his team. Sherrod then proceeded to march up this development curve, responsible for many of the milestones along the way. And those, as you can see from the labels here, relativistic optics, nonlinear QED, going toward a Planck limit of energy density, ultimately. Sherrod pursued these with an almost kind of Napoleonic zeal to make sure that this development was pushed and pushed very hard toward the physics that was possible to get by increasing the power density of the lasers. Now, our part of it in the materials science applications are basically this first step. Once you've got beyond 10 to the 14 watts per centimeter squared, which CPA allows you to do, then you're into a regime where dense plasmas can be produced. Plasmas that have basically solid state densities, metallic densities which are equivalent to solid metals, produced by a laser. And once you're in this regime, now you can think about how do you modify interatomic potentials using the excitation of the laser. So this is a very exciting development when this milestone determined by, described by that dotted line there, once that's passed, then it opens up a new regime of atomic environment which can be used to modify materials and to produce new materials with new properties, and they're mostly in the nano scale regime. So that's it's kind of a funny story up here. We're not really concerned with these very, very high power densities, but there was talk at the time as this development is going on, could this lead to like many black holes? Can you produce black hole at these kind of power densities? So a lot of talk about, oh, this is really dangerous research and blah, blah, blah. But fortunately, we haven't got anywhere near into that regime, which would be a much, much higher power density that's required to affect the gravitational quantum gravity using high fields produced by lasers. We're just concerned here with power densities that are on the order of 10 to the 15, which is already a very impressive accomplishment for lasers. So a lot of this materials work's motivated by the same thing that motivated the previous speakers in today's session, the need for better energy critical materials. For example, solar photovoltaics, improved energy storage in batteries, still one of the very, very important missing pieces in the energy material area. How do you make better battery electrodes? How do you store energy in supercapacitors, for example? Can these be used for transportation? We'll have a little bit more on that tomorrow. How can we recover waste energy using thermoelectric generators? Better sensors based on nanoscale materials, and so on and so on. Many, many opportunities that are opened up by nanoscale materials, and these are the parameters that everybody is striving to achieve: uniformity, reproducibility, lifetime, control over the stoichiometry of the materials, control over the form factor and shapes of nanostructures, as Sharon eloquently described this morning, and getting very high density of nanostructures into small volumes. All of these are really critical. So I'm going to, in this talk, I'm going to talk a little bit about nanopatterning using femtosecond lasers. What are the opportunities? What can these kind of lasers do for us? And these are lasers in that regime that I just shown you, just above the threshold where CPA, Chirp pulse amplification, can get you into those energy density regimes. How can film deposition be achieved using laser beams? And how can existing materials be processed in a way that can lead to new properties? And I'll talk a little bit about graphene as an example of that. So the theme of the talk here is really this plasmonic state which the laser can achieve, the CPA laser can achieve, and how excitation, coupled excitations between plasmons and optical fields driven by the laser can be used for nanofabrication. And we haven't got Palab yet to using the quantum dot lasers for this purpose yet, but we have been using another version of lasers based on fibers, doped fibers, which have the potential to have very high power density and average powers exceeding a kilowatt even. So we've been doing a lot of work with fiber lasers in this area, mostly because of their capabilities for high average power. And some of the advantages offered by these kind of lasers are precision pulse train control using optical combs. These are sequences of pulses that are put out by such lasers in a very precise way. The high throughput that goes along with the high average power of these lasers, exceeding kilowatts, as I said, allowing processing under ambient conditions rather than ultra-high vacuum, for example. And probably most important of all, opening up the possibility to do interatomic modifications of the interatomic potential using the field, the electric field of the laser, to modify the potential interaction between atoms, allowing for new structures to be formed. These would be formed transiently within the time scale of the laser pulse itself. And since the pulse is very, very short, then on a much faster time scale than thermal transport can occur, then this is basically a non-thermal process. In other words, it doesn't involve melting the material or completely dissociating the molecules and atomic configurations, but modifies the potential without producing huge amounts of entropy. So, a quick word about timescales. The cascade of energy transfer that occurs when a laser beam interacts with a solid is very advantageous in terms of being able to modifying the bonding potential. For example, electron-phonon coupling allows you to transfer energy from the laser itself into the solid through optical phonon excitations, primarily, which are excitations within a unit cell, which are important for modifying the potential. And the fast timescale there goes along with a short spatial scale, in the sense that if you look at the transfer of energy through a solid, basically at the speed of sound within the solid, it's about 1 nanometer per picosecond. And a picosecond is a kind of mid time scale that is easily accessible with these kind of pulse lasers. So, so you can think of a picosecond being equivalent to a length scale, a transport length scale of 1 nanometer. There are many processes that can be studied and manipulated with lasers on this range of timescales from femtoseconds to nanoseconds, some of which are of large interest for chemical processes, like molecular rotations, radiative decays, which Ted talked about earlier this afternoon. There are processes such as of interest for energy conversion, like electron transfer in photosynthesis in this range. There are phase transitions which occur, strain propagation and spin dynamics on timescales that are in this range. So these are extremely important tools for studying the basic dynamics of energy critical materials. I want to start with one example, which is related to the last thing that Palab was talking about, which was basically nanowire fabrication, which is relatively easy to fabricate in the vertical geometry through the so-called VLS method. And these kind of nanowires, as he described, very useful for laser structures, also useful for catalysis, biosensors, battery applications, and modification of electrodes to allow access to faster charging and so on. There's another geometry, though, which is a little bit more difficult, which is more kind of related to planar electronic geometry. In other words, building circuits on substrates and transporting digital information around on a chip surface, in which case you need horizontally aligned geometry rather than vertical. Lithography of these kind of devices rather expensive and somewhat cumbersome to perform. If you could do this in a kind of parallel fashion, instead of having to write structures on the surface, if you could have a way of producing nanowires on the surface in a reproducible fashion, in a controlled fashion, then that would be a big step forward. And what I'm going to tell you here is that, at least in the infrared regime, these femtosecond lasers can be used to pattern structures of that in that geometry. So let me just describe a little bit how this goes. So this, as a lot of developments go, this one was somewhat accidental, and we started basically with a antimony telluride film, just a epitaxially grown film on a sapphire substrate, and illuminated that with one of these femtosecond lasers. We were interested actually in looking at the spectroscopy of phonon vibrations in the antimony telluride and studying the the spectrum of that material. And what we found after we'd been doing these experiments is we started seeing these patterned structures which looked a little bit like this, although this is after quite a few, quite a lot of development of the method and the parameters to get nicely ordered nanowires, but basically we were very surprised to see this. Why were we so surprised? Because the size of our laser, diffraction limited to about three times the wavelength, which is about 3 times 1.5 microns, 4.5 microns in diameter. That laser spot was much bigger than the features we were seeing in the produced on the surface when we scanned this surface underneath the laser beam with the polarization of the laser oriented perpendicular like this, in other words, perpendicular to the scan direction. We saw very, very narrow wires of widths a little bit less than 60 nanometers, actually, and with a period of only 130 nanometers. And remember the scale here. This is 1 micron. So where does this scale, how come something is forming here with a scale that's much smaller than the optical diffraction limit of the laser spot? Before I get to that question, let me just say something about why were we interested in antimony telluride here? Well, firstly, because it has an infrared gap of about 0.3 eV, so it's in the mid-infrared region. There are many applications that are interesting for sensors in this region of the electromagnetic spectrum. The material also has a kind of intermediate bond strength. It's not a very strongly bonded material. It's perfectly stable, but it can be modified using using the electric field in a laser with moderate energy density. It also has a van der Waals gap. Every 5 layers here, there's a van der Waals gap. In other words, a weakly bonded package of layers, weakly bonded to another quintuple layer. And as you go down the c-axis here, then you have a series of layers. So this is a prototypical layered compound or quasi-2D material. It has interesting thermoelectric properties, which I'm not going to go into here. It's one of the materials that's used in high-performance thermoelectric devices. And it also is of interest from a solid condensed matter physics point of view in having what are called topological edge states, which I'm also not going to go into, but very interesting excitations involving spin propagation, which protects the transport from defects. So a lot of interesting things about this material, but our primary interest was for infrared applications. So there are previous talks talked about, for example, Ted Goodson's talk talked about the kind of information you can get from pump probe methods, spectroscopic measurements, which involve hitting the material with a narrow pulse, a time delay, and then a second pulse to probe what it was you did with the pump. And Halab's talk also had information derived from measurements like this about charge transport in the laser, relaxation time information, and so on. I'm not going to go into any detail about this, but this is an important part of the experiments that we do with these materials. It's called asynchronous optical sampling, what I just described, and it basically uses pulse widths on the order of 100 femtoseconds, center wavelength of about 1.6 microns, repetition rate about 100 megahertz. Now, one question is, why do we need such narrow pulses? We need those narrow pulses, according to Moreau's law, because we want to achieve a large density of free electrons. We want the laser to produce a plasma, and we want it to be a basically solid density plasma, which would be around 10 to the 22 or 10 to the 23 electrons per centimeter cubed, roughly Avogadro's number per centimeter cubed. So we published this. This is the first time that this kind of measurement had been done with fiber lasers, and we published this about 2009. One of the things we learned from doing measurements during the processing with the laser, one of the things we learned is that we indeed could modify an interatomic potential in this material, antimony telluride, by illuminating it with pulses from such a laser. And that was shown to us by this additional peak here. This had actually been reported just previous to our work, but it had been, fortunately, been reported as an incorrect result. It had been reported as an optical phonon excitation of the intact structure, antimony telluride. Because its position here is close to that of an EG optical phonon, but there's a small difference, as you can see here, between this new peak and the weak optical phonon, the EG mode, and that difference is crucial in interpreting this peak correctly. And what it showed was that we can actually use the laser field to modify the interatomic potential. And we can use that separation of the across the van der Waals gap to produce a layer of tellurium separate from the regular structure. And it's correctly identified here as an A1G optical phonon. So these kind of measurements done during the processing are really crucial, because otherwise, how would you know, how would you know what's going on? And you do something to the material, but you don't know what it is. Here, this gives you really good microscopic information. Also giving you really good microscopic information is something that we're very fortunate to have at Michigan, and that is a characterization lab with excellent electron microscopes, and not only excellent microscopes, but excellent experts in using those microscopes, like Kai's son, for example, who can do these kind of cross-sectional measurements, and I think some of Rachel's students also involved in these measurements to look in detail about what these wires, these wire-like structures that I showed you, what is the actual microscopic structure inside these wires. If you're going to do this kind of process, it's really important to know how to optimize it and to know in detail what's the physical and chemical characterization of the structures that are formed. And I want to point out here, and this is a really, this is like what you might call a smoking gun, and that is the shape of these structures. Remember, this started as a thin film here, a nice, smooth epitaxial film before we hit it with the laser. And now you see it's producing these very interesting shapes between what we're calling the wires here. In these valleys, they have very interesting shapes. And that is going to tell us, as I'll point out in a moment, what is the basic mechanism that produces these kind of nanostructures. So one of the things you can do with cross-sectional high-resolution TEM is you can look at the chemical makeup of the nano features element by element. Here's a map of tellurium, as you'd expect, within an antimony Telluride structure. Tellurium, antimony, bismuth, and crucially here, oxygen. It's telling us that the oxygen, even though the tellurium is concentrated within the wires, the oxygen, first of all, there wasn't any oxygen originally, it was just antimony telluride. Now we've got oxygen in there, and it's occupying sites between the wires. In other words, in these valleys between the wires, there's a substantial amount of oxygen. And the aluminum here is from the substrate, obviously. So this tells us there's something chemical going on as well as physical. And then it was time to look in even more detail and really get down to details where we can see individual atomic layers. So this is a nanowire region. And these, I don't know if you can see this where you are, but these layers here are the quintuple layers separated by van der Waals gaps, and there's a blow-up. There's a zoom in here where the darker regions are the van der Waals gap, and then there's 5 layers, and then another van der Waals gap, and so on. So what's really interesting is that within the wire region, there's a perfectly ordered antimony telluride, just like it was when we grew the film. So this part of it is undisturbed, with perfectly ordered quintuple layers, as you would expect. Between the wires in the valley, and this is where we saw the oxygen, it's not anywhere near as nice. It's highly disrupted into grains with these dashed lines here indicating individual grains. And the zoom in on that shows us that we have different orientations, whereas this was perfectly ordered. This has got 011 orientation. This is 1 bar, 2 bar. And not only that, it's not antimony telluride anymore, it's antimony oxide. And that means that all the tellurium that was in these valley regions was exchanged for oxygen from the atmosphere in which we did the laser illumination. So instead of antimony telluride, we now have antimony oxide. Antimony oxide happens to be an insulator, and that means that since the nanowire, being a very narrow bandgap material, is highly conducting at room temperature, almost like a metal, and that shows that we have actual wires separated by insulating regions all the way down to the substrate. So what's the mechanism that causes, that leads to this kind of structural and chemical change? There are a couple, by the way, this is still an open question for further research. This interaction of high field lasers with solids still not perfectly well understood. There are a lot of mysteries remaining. And some light is being shed on this. Sorry about the pun. Some understanding of the basics is starting to emerge. For example, this paper by Huang in EECS Nano, it's a highly cited paper, talks about a coupling between surface plasmons and the laser grading. In other words, the optical field of the laser produces coherent fringes on the surface of the material. The laser produces a plasma, as I've discussed. That plasma can couple to the optical field of the laser, and it can produce additional periodicities and length scales that are more appropriate of the surface plasmon length scale, which is much shorter than the laser wavelength. And that coupling can actually modify the potential in different parts of the optical field. In other words, when you have a maximum, imagine the laser as a sine wave, giving a sine wave. On the peak of that sine wave, you have a very high field. and that can drive the potential changes, interatomic potential changes, whereas at the minimum of that field, then that will leave part of the structure undisturbed, and that's what we see here. And the surface plasmon can have the effect of coupling into that and causing, as you increase the number of pulses that the laser delivers to the structure. This is a log scale here, so this is starting to die here. So this is 10 pulses delivered, 100, and so on. And what you can see here, this is the change in wavelength of the wires that are produced, the periodic spacing between the wires actually decreases. In other words, getting more and more high frequency, spatial frequency. And as you keep delivering more and more pulses, that wavelength shrinks down, which is the falling curve here. And what's happening here is the structure is becoming unstable to modulations, spatial modulations, driven by the laser field. And this decrease in wavelength here is very indicative of plasmonic coupling, as shown by this series of measurements here. And it's not just in one particular material. Antimony telluride is rather, you might consider, a rather exotic material, but it's also seen in things like, simpler things like zinc oxide, zinc selenide, silicon carbide, diamond even, which is very strongly bonded, graphite, and copper zinc alloys. So it's a very general phenomenon driven by a coupling between a plasmon and an optical field. So this is also consistent with those, you remember those complicated shapes that I was telling you about, which we wondered about. And for example, right here, this particular shape in the valley region is what you'd expect if you had a dielectric constant discontinuity, which leads to locally high field regions being set up inside the material driven by a plasmon, a plasma oscillation, which is a resonant oscillation of the free electron density, and it can give rise to these kind of complicated shapes where there's a dielectric discontinuity. So this is highly consistent with the plasmon mechanism. That's why I call this a smoking gun. I'll mention another paper. Steve Yelosov's one of my collaborators, and Ben Tralva here in the MSc department. They came up with a very interesting observation recently in which there's a bifurcation occurs in the period of these surface oscillations driven by a laser. And they've associated that with a defect or vacancy accumulation in the material. This is basically a strain-driven mechanism that forces all the dislocations into a localized position between the between the valleys here. And after a given number of pulses, this can deepen where the vacancy and the strain is highest, and you can actually get a modification of the potential there due to the accumulation of many vacancies. And this can get deeper and deeper, and it can actually double the periodicity of the wire period as the number of pulses increases. So again, this is showing that there's a coupling between the optical field and the electron density of the material in a very interesting way. So there are a lot of details here. How do we know? We got antimony oxide instead of antimony telluride in the space between the wires. In other words, an insulating valley. We do very detailed phase identification from the transmission electron microscopy, looking at lattice spacings, matching those to compounds that are formed. We also do a lot of X-rays to back that up. So we see X-ray peaks from antimony oxide, and also, of course, from antimony telluride from the wires themselves. One of the really nice things that came out of this work was done by Jana Waldrath, who's now graduated from Rachel's group, doing scanning tunneling microscopy, scanning tunneling spectroscopy experiment, where Jana took a wire. This is a really difficult measurement. She scanned an STM, scanning tunneling microscope tip, across the wires in the transverse direction to pick up what is essentially, this is the di by dv, the slope of the IV curve, which tells you about the density of states in the material as you're scanning across. For the nanowire region, got a very narrow band gap. Essentially, the region around 0 here would have a very low density of states if it's an insulator, which is seen in the valley region with a band gap that's at least 3 eV. So it's essentially an insulator at room temperature. Whereas in the nanowire region, that measurement returns the infrared band gap, which is about 0.3 eV in the region of the wire itself. So the pattern of spectroscopy that Jana got alternates between an insulator and a narrow band gap semiconductor as she goes from the wire to the insulating region and then back to the wire. So very, very nice measurement. I don't know how long it took, weeks, months to improve the data and the sample preparation to achieve this, but it was worth it to just nail the measurement finally. Yes, there are wires, and yes, they have insulating regions between them. I want to look at, how long do I have?
What time did you start? A little before 4. So yeah, time is almost up.
Huh?
Time is pretty much up.
Okay, so let me very quickly. We've heard a lot about the unique properties of semiconductor nanoparticles which can also be produced by these lasers. And in particular, one can modify the effective band gap of these materials by changing the diameter of the nanoparticle. One can increase the band gap by making the diameter or the radius here smaller. And this suggests a way to electronically tune the semiconductor nature of the nanoparticle to match various requirements, for example, to match the peak in the solar spectrum if you're interested in using nanoparticles for energy harvesting. The unique singular nature of the density of states already been described by several workers so far. So we set up a system to deposit films of nanostructures. To my knowledge, this is the first example of an actual film composed entirely of nanostructures. And we did it using, again, a narrow band gap infrared material, germanium, with a target of germanium illuminated with a high power laser producing a plume which deposits a film on the substrate. I'll just show you the kind of bottom line of the measurement. We do get nanoparticle, copious amounts of germanium nanoparticles. They're well crystallized. They have a mobility of more than 100 centimeters squared per volt second. Those are highly interesting for PV applications. They're way bigger they're not as big as the bulk germanium mobility, but they're actually way bigger than amorphous materials and polymers and so on. And free charge density is on the order of 10 to the 17. So what's interesting about this is that one can actually get a semiconductor material in nanoparticle form that has an effective band gap that is quite a lot larger than what you have in the bulk. This is the bulk, the dashed line, and it's blue shifted over by a substantial fraction of an EV, almost to the point where silicon has its band gap. So in other words, you created a material which has properties that are somewhat intermediate between germanium and silicon by making it into a nanostructure. This is not just one particle, it's the average of a whole macroscopic number of nanoparticles deposited as a film with an optical absorption curve, or transmission in this case, that is intermediate between between germanium here and silicon here. This could be quite useful for solar, tandem solar cell applications, where you make an additional layer in the photovoltaic material to capture infrared, which is where the majority of the solar spectrum occurs. Okay, one other example, which I don't think I have much time to talk about here, is modifying graphite to achieve exfoliation, in which case you would be able to produce graphene, single carbon planes known as graphene, keeping the structure within the planes intact. So this is a way of producing graphene using a laser, and what it overcomes is the van der Waals coupling between the planes, which is about 43 millivolts per atom, per carbon atom. And these lasers are quite capable of producing this amount of energy per carbon atom, lifting the planes away from each other and allowing you to use the large surface area of graphene to excuse me, to improve the coatings on electrodes for batteries. So the idea here is take a battery electrode, coat it with graphene so that it can store more charge and so that it can charge can enter the battery more easily, and so its cycling would be improved. So we've improved the cycle lifetime of a battery by a factor of 1.6, which is huge, just by taking graphite, exposing it to a laser after it's deposited on the battery electrode, and allowing the battery to have a much greater lifetime and many, many more cycles is one of the limitations of battery technology. You can't cycle them as many times as you would like. This extends the lifetime by a factor of 1.6. And it can be done quite simply, just scanning a laser line focus across a graphite-coated electrode, producing graphene sheets. This is an SEM picture of that, showing that we have transparent sheets with very, very large surface area. Some similar measurements that the batteries can also store more charge when they have this kind of electrode produced with a nano processed graphene. So I just want to acknowledge some of the people who contributed to this work. My collaborators across the U of M, Rachel, Kevin Pipe, Kai's son, I mentioned, his expertise in TEM has been really crucial. My colleagues Stuart Ewer in physics, John Neese in the Center for Ultrafast Optics, Max, Joanna, Steve Yalosov and Ben Terhoever I mentioned, Alec Thomas in nuclear engineering, and Vladimir Stoiker who's now over at Argonne Labs, and especially these three graduate students who did their PhDs in this area. My student Abe Orca and Yue Li, who graduated last year, and Jana, who did the very nice STM work from Rachel's group. And our funding sources, Department of Energy, National Science Foundation, and U of M, through graduate support in the applied physics program. So conclusions, I'll leave that up there. If there are any questions, I'd be happy to entertain those, and thanks for your attention.